So hi, my name is Sacha, and today I'll be presenting Spectrum, a high bandwidth anonymous broadcasting system, and this is joint work with Zachary Newman and Devadas. So the motivation for Spectrum is that whistleblowers in society expose corruption in both governments and corporations, but they often do so at a great cost. Many are fired from their jobs, some pay with their lives, and some go to jail. And so it's perhaps no surprise that many whistleblowers wish to remain anonymous when publishing documents. So how can whistleblowers publish documents anonymously? Well, if they send it to a server like held by the New York Times, for example, then the New York Times could publish it. But this requires trusting the New York Times server. So instead, what whistleblowers can use is a system like Tor to hide in a crowd and sort of obfuscate the source of the broadcast file. However, this introduces another problem, which is that Tor is susceptible to metadata leakage, which means that a powerful adversary controlling many, like a CDN, an ISP, for example, can figure out who leaked the document. So Spectrum tries to solve this problem. And the setting in which we work in is we'll have many users who are connected to Spectrum and relatively few broadcasters who are trying to publish files anonymously through Spectrum. And we're going to have two non-colluding servers, two or more non-colluding servers that will help achieve this goal. And this is a similar model to recently built system collaboration between Mozilla and Meta, where they have used two non-colluding servers for privacy as well. The threat model in Spectrum is that one of the servers can be malicious and arbitrarily deviate from protocol, and no client in the system will be trusted. The goals we want to achieve under this threat model is that we want to have anonymity for the broadcaster within the set of all honest users, and the way you can think about this is kind of like plausible deniability. We want metadata privacy, which means that even if an adversary is observing the entire network, they cannot tell who sent the broadcast file. And we want security against malicious clients and a server deviating from protocol. So a strawman solution to anonymous broadcast, a relatively old solution by Chom from 1988, uses secret sharing and this two non-colluding servers to broadcast files anonymously. So the idea here is that each client can secret share their document by sending secret shares to each server. And individually, these secret shares don't reveal anything about the file to either server. However, the servers can recombine the shares to recover the broadcast file. And all other clients in the system will provide cover traffic by just sending secret shares of 0 to obfuscate the source of who sent the file. Once all these contributions, secret shared contributions, are received from the clients, the servers will aggregate them into these aggregate shares, and then they can post them to a public bulletin board, and these aggregated shares will recover to the broadcast file that was sent by the broadcaster. So while this does obscure the source of the broadcast, there's a problem, which is that malicious clients can disrupt the broadcast. So to see how malicious clients can disrupt this, recall that a broadcaster will secret share their file. Honest clients are supposed to secret share 0, but nothing is preventing a malicious client from just secret sharing a bunch of garbage values. And because these secret shares are random, the servers can't tell if they received a bad value. And so what will happen then is that the servers will aggregate these shares as before, but now the recovered shares will just be corrupted. And this is by the properties of the secret sharing. If the malicious contribution is aggregated in the secret share, then the recovered value will be garbage. So to prevent this, we want some kind of blind message authentication. Specifically, we want to make sure that each share is either a secret share of 0 if it's coming from a client just sending cover traffic, or that the user is authorized to be broadcasting a non-zero message. And for now, I'll only consider a setting with one broadcaster, and I'll generalize later to multiple broadcasters. And so what we want is the servers have to perform this check over the secret shares in zero knowledge. And what's important is that this verification doesn't reveal whether or not the share was a share of 0 or a share of a file. And this must hold even if one of the servers is malicious. So to kind of illustrate the functionality, if we have some kind of access key that's known to the servers, and the broadcaster also has this broadcast key, then the broadcaster can send a secret share of the message, and the servers will accept that contribution. And likewise, for a client just sending cover traffic, if they send secret shares of 0, even if they don't have knowledge of this access key, then the servers will accept the contribution. However, if the client is trying to send some garbage values, the servers will reject. And this must hold even if the client has some kind of bad key that isn't the correct key used for authentication. So fortunately, prior work solves this. In Express, they use zero-knowledge proofs to achieve a similar functionality. The idea there, just illustrating how it would work for a broadcaster, is that the broadcaster will generate a secret share of the message and secret shared proof. It will send these values to the servers. And then the servers and the client run this lightweight multi-party computation to check that the proof is valid. However, this requires multi-party computation with the client, so it requires some interaction with the client and the servers. And perhaps more importantly, it's not secure against a malicious server just sharing the key with a malicious client to covertly disrupt the broadcast, as I explained before. So in Spectrum, we take a different approach. We use a Carter-Wegman MAC. And the nice thing about a Carter-Wegman MAC is that it can be computed locally on secret shares of the message. And this is an observation due to prior work. So what does this mean? Is that if we have a secret share of a message, the servers can multiply the key, the secret share with the MAC key, and they get a MAC tag T, which is also going to be secret shared. So how can this enable blind message authentication? Well, if a broadcaster has this MAC key K and the message M that they're trying to send to the servers, they can locally compute this tag T using the key. And then they can secret share the tag T and the message with the two servers. The servers can locally recompute the tag using the key to get a tag T hat. And then they can compute this check value C, which is just going to be the difference between the provided tag and the recomputed tag. And then all they have to check is that this value C is 0, and they can do this by just recovering their shares of C. And intuitively, what's going on here is that the servers are just checking that the client had computed the right tag for their message. But how does this work if a client is just trying to send cover traffic? Well, the nice property of this MAC is that for the message 0, the tag is always going to be 0. So a client sending cover traffic can just secret share the tag T equals 0. And then the servers will proceed as before to recompute this tag T hat, and will also compute the check value C. But in this case as well, the check value is going to be 0. And so the servers in both cases, whether it's a broadcaster or just a client sending cover traffic, will recover the value C equals 0, and they can't tell in which scenario they're in. So to recap, we use this MAC to check the statement that either the secret share provided by a client is 0 or the user has knowledge of the secret key. And in Spectrum, to prevent this attack where a malicious server just shares this MAC key K with a malicious client, we have two keys. We have a public key, G to the K, where G is a generator for a group in which the discrete logarithm problem is assumed to be hard. And then we have the MAC secret key, which is known to the broadcaster. And then we essentially just take all the verification I explained before, and we just shift it to the exponent of G. But I'll leave the details to the paper. OK, so now that we have that working, how can we have support for multiple broadcasters? Well, so essentially what we want is we have maybe L broadcasters trying to send L different files. And we can naively do this by just repeating the strawman protocol I described before L times. Now, this has the unfortunate side effect that the overhead for each client is going to be linear in the number of broadcasting users in the system, because they have to send cover traffic for each instance of the strawman protocol. So if we have L channels, where a channel is just some space allocated for a broadcaster to share their file, then the bandwidth overhead will be O of L. So the observation here that allows us to reduce this overhead per client is that each write is essentially going to be a one-hot vector, where the broadcaster will be writing 0 to all the channels except to the channel that is allocated to them. For coverage traffic, the clients will just be sending the all-0 vector. So this is just a generalization of the strawman protocol I described before. And so what this allows us to do is use a distributed point function to compress these secret shares of these one-hot vectors into a logarithmic number of bits. So we went from linear to logarithmic overhead. And this is a similar technique used in prior works, notably Riposte and Express, to also compress these secret shares of these writes. Okay. So however, in Spectrum, we want to make sure that the message authentication I described before works in this vector-based setting. So specifically, if a client has a key for the 3rd channel, they shouldn't be able to write to the 5th channel, for example. And we also want to make sure that a client just sending cover traffic, notably the all-0 vector, can always write to all the channels. And so in the paper, we show how the technique I described before kind of generalizes pretty naturally to this vector-based setting. However, there's still one more problem we have to solve. And that is the fact that a malicious server can exploit the MAC verification to eliminate clients. And so how does this work? Well, if we recap how blind MAC verification works, after a client secret shares their message with the servers will compute these the MAC tags and check that the shares are authenticated. The problem with this is that a malicious server can just substitute the share it received from a client for some garbage share that it comes up with itself. And in this case, the verification computed by the 2 servers will fail, and this client's contribution will be eliminated. Now, the problem with this is that if the server that substituted the client's share guessed who the broadcaster is correctly, then the resulting value will be 0 because the broadcaster's contribution was not aggregated into these secret shares. And so what this reveals is that the eliminated client was actually the broadcaster. So the malicious server learns that the client it eliminated was actually trying to one of the broadcasters. In the paper, we solved this with a new protocol we call blame game, which will assign blame to either a malicious server or a malicious client. And blame game has a very small overhead per each request. And the cool thing with it is that it actually applies to other anonymous communication systems to prevent similar styles of attacks. However, I don't have time to cover it, so please see the paper for details. So comparing Spectrum to related work, if n is the total number of users in the system, and L is the number of broadcasting users in the system, Spectrum achieves an overhead per user of logarithmic in the number of broadcasters, not the total number of users. Comparing this to prior work in anonymous broadcasting, the overhead of those systems is actually square root in the number of total users. So this is a significant improvement over Riposte and Blinder. Additionally, Spectrum protects against this active attack by a malicious server with blame game, whereas prior work, notably Blinder, protects against this with multi-party computation, so they require an honest majority of 5 out of 5 servers to have the same security level. So one way to think about this is that previous systems are kind of like anonymous Twitter. They assume everyone is broadcasting, which makes them only suitable for low bandwidth content. And Spectrum is more like anonymous Twitch. It assumes that the number of broadcasters is much smaller than the number of total users, and this allows Spectrum to support high bandwidth content. The network overhead in Spectrum is only about 200 bytes over non-private broadcasts. So in our evaluation, we find that Spectrum is really fast with 1 channel and really big messages in the megabytes. On the x-axis, we have the size of the message. With 10,000 clients, Spectrum can process all these clients in about 40 to 100 seconds with up to 5 megabyte messages. And this is 4 to 7 times faster than Express in the same setting. Spectrum remains fast even with many channels. So with kilobyte payloads, so kilobyte messages, and 100,000 clients with 1,000 of those clients broadcasting, Spectrum is 60% faster than Express, 4 times faster than Riposte, and up to 20 times faster than Blinder. However, as the number of broadcasters becomes larger out of these 100,000 users, then other systems might become more competitive, as we can see as we go right. However, as the message size gets bigger, Spectrum outperforms these other systems. That's it. I'm happy to take questions.